air-cooled engines, oil-cooled engines, and liquid-cooled engines. You must have heard these names. And as their names suggest, these are different types of engine cooling systems. And in today's video, we will understand how these different cooling technologies work, what differences they have, and we will also see their advantages and disadvantages. We know that when an engine runs, it generates heat along with mechanical work. On average, an engine converts only about 30% of the fuel's energy into mechanical work. The remaining energy is wasted as heat. Now, if this heat is not controlled, the engine parts may melt, and the engine will seize. That is why we need engine cooling, and the cheapest and simplest cooling method is air. To understand air cooling, first we need to understand the basic principle of heat transfer. Whenever a hot surface comes in contact with cold air, heat automatically starts transferring from that surface to the air. This process is called convection, in which heat transfers from a solid surface to the surrounding fluid, which in this case is air. The greater the temperature difference between the surface and the air, the faster the heat transfer will be, and the larger the surface area, the more heat can be transferred. So, in simple words, if we want to cool a hot object quickly, we need to increase its surface area. Imagine a plain metal sheet. The air will just pass over its top surface. But when we add 10 to 15 fins on it, the same air flows through each fin. This concept is implemented in an engine as well. On an air-cooled engine's cylinder block, there are many thin metal plates or ridges. These are called cooling fins. This increases the engine's effective surface area many times. The larger the area, the more air will pass through these fins, and the faster the engine heat can escape. So this becomes a very simple and inexpensive cooling system. But air cooling also has some limitations. Air cooling works best only when the outside air is cool and the airflow speed is good. When the bike runs on the highway, continuous high-speed airflow passes over the fins, and the engine keeps cooling effectively. But if you are standing in traffic during summer, fresh air cannot reach the engine fins, and proper cooling cannot happen. And this temperature fluctuation directly affects combustion efficiency, fuel economy, and engine longevity. That is why large and high-performance engines cannot rely only on air. Look, air can cool the engine from outside, but internal parts like piston and valves where outside air cannot reach. To cool these hot spots, we use something that is already present inside the engine: engine oil. And that gives us oil-cooled engines. Normally, engine oil is used to lubricate the parts so that friction remains low. But oil can do one more job, which is absorbing heat from the engine's internal parts. But engine oil is also used in air-cooled engines. So what is different here? In oil-cooled engines, an additional component is added: an oil cooler. An oil cooler looks like a small radiator which is generally mounted at the front of the engine. When oil comes in contact with hot engine components, it absorbs heat through conduction. So here, oil is not only doing lubrication but also acting as a heat carrier. This hot oil then leaves the engine and goes into the oil cooler. When the bike moves, air flows through the oil cooler and cools the hot oil. Then the same cooled oil goes back into the engine. Now, with the help of engine oil, we solved the cooling of internal engine parts. But one problem still remains. Just like air-cooled engines, in oil-cooled engines as well, we still depend on outside air to cool the cooler. And if your bike is standing still, air will not pass through the cooler. Result, the oil will not cool down. So, if we want to maintain the engine within an exact temperature band, whether in traffic or on the highway, we need an actively controlled cooling system. And that is exactly what a liquid cooling system does. Now, technically, oil is also a liquid, but oil's heat-absorbing capacity, that is, specific heat capacity, is lower compared to water. In simple words, the same quantity of water can absorb more heat than oil.
In older vehicles, plain water was used for cooling, where water had to be refilled in the radiator frequently. The reason was that at that time, the cooling systems were mostly non-sealed and non-pressurized, meaning the pressure inside the radiator was almost equal to atmospheric pressure. And there's a simple rule in science. At normal pressure, water starts boiling at 100 degrees Celsius.
So, when those engines became hot, the water reached its boiling point and started boiling. Then the water converted into steam, and the steam escaped through an overflow pipe. Because of this, the radiator water level gradually decreased, and we had to refill water again and again. And the problem was not limited only to boiling. With plain water, there was also risk of rusting, corrosion, and freezing in low temperatures. So to solve this problem, cooling systems were made sealed and pressurized, and instead of plain water, coolant was used, which is a controlled mixture of water plus some chemicals that provide corrosion resistance and antifreeze properties. You may have seen some pressure ratings written on modern radiator caps. This tells you that the radiator is pressurized. Inside this cap, there is a spring-loaded pressure valve which maintains about 1 to 1.5 bar pressure inside the system. When pressure increases, the boiling point of the liquid also increases. That is why, in a pressurized system, coolant can remain in liquid state even at 120 degrees Celsius or higher temperatures. Now, let's see how this coolant actually cools the engine. To use coolant, hollow passages are made around the cylinder block and cylinder head of the engine. These are called coolant jackets. When the engine runs, high temperature is generated in the combustion chamber. Heat then reaches the cylinder walls through conduction. The coolant circulating around the cylinder wall absorbs this heat. A water pump continuously circulates the coolant. The hot coolant leaves the engine and goes to the radiator. Inside the radiator, there are many thin tubes and fins. Coolant flows through these tubes, and heat transfers from the coolant to the tubes, then from the tubes to the fins, and finally from the fins to the air through convection. If the bike is moving, natural airflow does the cooling, and if the bike is standing in traffic, for that condition, a radiator fan is installed, which continuously blows air through the radiator. But this system has another interesting point. If during a cold start, coolant starts circulating through the radiator from the beginning, the engine will take longer to warm up. That is why this system uses a thermostat. When the engine is cold, the thermostat remains closed, so coolant does not go to the radiator, and the engine can reach its optimal temperature faster. As soon as the engine reaches the optimal temperature, the thermostat opens, and coolant starts circulating through the radiator. So, the liquid cooling system not only removes heat, but also helps the engine operate within a controlled temperature band, whether it is traffic or highway. Now, finally, if we compare these three systems, air cooling is the simplest system. No pump, no radiator, no coolant. Lightweight, low cost, low maintenance. But it completely depends on airflow, and temperature can fluctuate in traffic. That is why this system is mostly used in commuter bikes and low compression engines. Oil cooling is an intermediate solution. It is more effective than air cooling because oil can reach internal hotspots. But it still depends on airflow, and oil's heat-carrying capacity is also limited. And finally, liquid cooling is the most stable and controlled system, which is ideal for high-performance and high-compression engines. So, with this, we end this video here. If you have thoughts or suggestions, do share them in the comments. See you in the next video. Thanks for watching.